introduction by Jaskaran Singh, Karthik Kallakuri, and Kwan. So, the aim of our project is to use standard hospital testing and specific classifiers gathered from patients to predict whether a person has diabetes. Accurately detecting diabetes can improve patients' health through preventative care and medication, ultimately providing a higher standard of living for the patients. So, this data will help create a system that can confidently recommend further testing to catch the disease early and also identify potential risk areas and habits that can be prevented. The final response variable is whether the patient has diabetes or not. This dataset has been collected using direct questionnaires from the patients of Sylhet Diabetes Hospital in Sylhet, Bangladesh, and has been approved by a doctor. Over to you, Kwan.
That's me. I'm Karthik, and I'm
Karthik,
gonna
yeah,
take it
sure.
from here.
Yeah.
So our problem statement. Our project is focused on classifications. For our classifications, we decided to use three methods: the random forest, K nearest neighbors (KNN), and naive Bayes. The data set we decided to use was early stage diabetes risk prediction. It was from the machine learning repository that we were recommended to use. So why did we choose this data set? Well, the reason we chose this data set is because as a team, we wanted to work on healthcare, and most importantly, we really wanted to do a classification models. So, with this data set, what is our goal? Our goal for this project is to classify different patients that are on the data set, whether they have diabetes or not, based on different features of the data set.
Mm.
Nice. So this is for our data set. This data set contains 520 observations, 17 features, with most of them categorical, with one as yes, two as no. Our target variable is class, and these are all our variables that I can see. We have age, where one is it's 20 to 65. We have sex, we have polyuria, polydipsia, we have sudden weight loss, weakness, and various other features, and we mark them with one for yes and two for no. And of course, for sex, we decided to go with one for male, two for female, and one for positive and two for negative for class. Next slide. So the methods we used, we decided to use three different methods as mentioned before: random forest, k-nearest neighbors, and naive Bayes. I decided to do k-nearest neighbors. Kwan decided to do naive Bayes, and Josh gone with random forest. The reason we decided to do these three methods, well, these are very commonly used algorithms and for classification. And these are the methods that we believe that we are most familiar with, so we decided to go for. And also they work well for our data set and for algorithms. Yes.
Okay. Next one, my name is Paul, and I will do presentation about data pre-processing and visualization. And as you can see, we just load the data set into a data frame. Then we use the dot head function to take a look at it. We can see the first five observations here, which contains all the features. We then use dot info function to have a summary about our data set. And using this function, we can also notice if there is any missing value in the data set. And as we can see, we don't have any missing values. Um, and since our data is mostly categorical, if we use describe function right now, it only shows the age features. So to deal with these type of situations and ensure that they work well with the machine learning models, we decided to create mapping for the categorical variables. And here we're using 1 for yes, for male for positive, and 0 for no, for female, and for negative. Now, after finishing mapping the variables, we can use this graph again, and then we can see have a better look at our data set.
Excellent.
Yeah, this one. So for visualization, we would just do some graphs to explore the data set and see the relationship between the features and the target variable. So the first graph we do is the count plot for the number of patients who have diabetes and who don't. And from the graph, we can obviously see that there are more people who have diabetes than people who don't. So there's a slight imbalance in the data, and which this might affect KNN. For visualize, we then visualizing the relationship between age and diabetes. The purpose of this is to see how do we grow will affect our risk of having diabetes. So we create an age range group, as you can see, from 0 to 10, and then 10 to 20, 20 to 30, and so on. And then we will group the data by age range and the target variable, which then will be plotted with a bar plot. The result is displayed, and we can see that as people get in the age of 30 to 70, they really have a high chance of getting diabetes than people from the age from 0 to 30. So yeah. Next thing, we're going to create some more count plots to see the relationship between some specific features to our target variable. So these graphs are created by count plots, and the features we are choosing are gender and obesity, which the for the gen oh, my bad. For the gender plot, male is 1 and female is 0. And as you can see, we can agree that the gender is a significant factor in predicting diabetes. By observing it, we can tell that the number of women having diabetes is much higher than women without diabetes, why the distribution is more even in the men's group. And below that, from the obesity graph, there isn't any significant difference in the distribution or having diabetes between the two groups. So we can believe that obesity is not a strong factor in predicting diabetes. Also, we also create a heat map. It helps. We also create a heat map to display the relationship of the features and the target. So it's a heat map of correlation matrix. And from the heat map, we find out some of the features that are strongly connected to the class variable, which are gender, polyuria, polydipsia, sudden weight loss, and partial paresis. Uh, for splitting and scaling the data, we use min-max scaling to scale our features, which is a very important step because we want every feature to influence the model equally. When we have separate training and testing data sets, we should fit the scalar to the training data only. The minimum and maximum values of each feature column should be determined based only on the training dataset. After that, we use the same scaler to transform both training and testing data. This will ensure that the testing data doesn't influence the training data.
Over to you, Karthik.
Okay,
Oh, the
so I'm gonna take it from here. This is the model I worked on, which is the KNN. So to start up with KNN modeling, we first decided to plot all for the first 14 Ks, get which has the best score, and once we get the best K using the graph, we can fit and find the score using that K. And as you can see, this is the code for the model. Next slide. So after we decided to plot the graph. We have this. As we can see, K equals 7 has the best score among our after 2. So we're going to use K as 7, and we're going to fit in score. Next. Okay, so as we see, we are using K equals 7. We decide to create K neighbor classifier, which will then fit and score. And after we fit and score, we see that we have a score of 0.9038. And yeah. Nice. So after that, we decided to get our confusion matrix to see to get all the see our model. Our accuracy is 90, which is pretty high, realistic, and reasonable. But is it the best? We'll find out.
Over to you, Kwan.
Okay. Naive Bayes is the method I use. Well, the first step of all is to create our model and then train the model on the training dataset. And you can see the code here. The next step is to use the test set to evaluate the model by making predictions and printing the result of the model's performance. And to see if there are any sign of overfitting, I print out the accuracy score for the training and the testing data. And as we can see from the code, they are quite similar in value, so there are no sign of overfitting. And next, after one I'm sorry. Next, we print out the confusion matrix because this is also one way to evaluate our model. They would display the true, false negatives and true, false positive values, and this will help us to observe the number of times the model predicts correctly and incorrectly. And I also add a heat map so that we have a better visualization of the matrix. And from the graph, we see that the number of true positives and true negative are the highest, which indicates that our model has a high accuracy in predicting the target. And then classification report is another way to evaluate the model's performance because it contains precision, recall, F1 score, and support scores. So we will print these out and use their values to make our decision. And based on their values, the precision, the recall, the F1 score, which are very high, all of them are above 0.9, we can conclude that the model performs really well in predicting the class of the patients. There's another additional step that I use. It is the K-fold cross-validation. This using tenfold as a number of K because this is common and popular when performing cross-validation. we will have a list of the score across the data set and having finding the average of these scores will give us the expected accuracy of the model. And we can use this to compare with the accuracy of the model using the accuracy score function. And as we can see, the average k-fold scores I got is 0.892, and the accuracy score I got from the function accuracy score is 0.91, and they're pretty similar, so we're pretty confident about our model's accuracy is around zero point 0.9.
Okay, I'm Jaskaran Singh, and I worked on the random forest classifier. So the first step was to find the optimal parameters of the model. We performed a grid search to optimize the model's performance. The grid search fits the model on the training data for each combination of hyperparameters, as you can see in the code, and evaluates its performance on the validation set. And the default value we used is fivefold cross validation. And once it finishes the grid search, it returns the best hyperparameters that maximizes the average accuracy score across all cross validation folds. So the parameter we tuned include n estimators, which is the number of decision trees that the random forest uses and the model creates. We use max depth, which controls the maximum number of levels in each decision tree. Min samples leaf, which controls the minimum size of the leaves in the decision trees. And min samples split, which controls the minimum number of samples required to split a node. Out of these parameters, the best parameter was chosen with the highest accuracy score, and this was chosen to be fit on our random forest classifier for the dataset. So once we found the best parameters, we fit the random forest on the training data and output the training accuracy score. We also did the OOP score, or the out of bag score, and test accuracy score. And as you can see in the output, since there is not much difference between the training and testing scores, this means our model is not overfitting the data, as there is similar performance on training and testing, and will generalize well on unseen data. Now the classification report and confusion matrix for random forests. Quick definitions. Precision is the proportion of true positive predictions out of all positive predictions. In other words, it measures how often the model is correct when it predicts a positive class. So in our case, for the random forests, the precision for class 0, which is not having diabetes, is 0.97. And for class 1, it is 0.93. Then for the recall, which is the proportion of true positive predictions over all actual positive instances, it measures how often the model correctly identifies positive instances. In our example, we had recall for class 0 as 0.85, and class 1 was 0.99, which is very high. So next was the F1 score. This is just a harmonic mean of the precision and recall. It's a balanced measure that combines both precision and recall. In our example, the F1 score for class 0 was 0.9, and for class 1 it was 0.96. As we can see, the class 1 was predicted better by the random forest. Overall, the accuracy of the model is 0.94, which means it correctly predicts the class. It correctly predicts whether the patient has diabetes or not for 94% of the test cases. You can see the confusion matrix. 1 is predicted much better than 0. Okay, conclusion. After comparing all 3 models' test accuracy, we found that the random forest classifier and naive Bayes performed better than the KNN. Random forests had the best accuracy of 94%. Since the dataset had mainly categorical variables, we expected models like naive Bayes and random forest to perform better than KNN. These models can handle categorical variables well and are known for their interpretability. There could be multiple reasons why naive Bayes and random forests might perform better than KNN for a dataset with mainly categorical features. One is that KNN is highly sensitive to the curse of dimensionality, which means that as the number of features increase, the distance between points in the feature space also increases. This makes it difficult for KNN to accurately identify similar points in high dimensional feature spaces. On the other hand, random forests are able to handle high dimensional data because they use decision trees as their base models, which can effectively partition the feature space into smaller subspaces. This can help reduce the complexity of the problem and prevent overfitting. KNN can also struggle with imbalanced datasets, where one class is much more prevalent than the other. So in our case, that we had more patients with diabetes. This is because KNN assigns labels based on majority class in the K nearest neighbors, which can lead to misclassification of the minority classes. Naive Bayes and random forests, on the other hand, can handle imbalanced datasets better and provide more accurate predictions for minority classes. Naive Bayes is relatively robust to class imbalance because it relies on probabilities of each class rather than the absolute number of examples in each class. Random forests can handle imbalanced datasets by adjusting the weights of the samples during training, which gives more importance to the minority class. Additionally, the randomness in the sampling of features and samples during training can help prevent overfitting to the majority class. That was it for our presentation. Thank you so much.
Thank you so much.
Thank you so much.